There is a molecule floating through space right now, in numbers so vast that a single dark cloud between the stars contains more of it than every gram of gold ever mined on Earth. But bring that same molecule down here, into this room, into normal air, at normal pressure, and it will destroy itself in under a second. Not evaporate, not react with the air, destroy itself. Today I'm going to show you exactly why, and by the end of this video, you'll understand why chemists spent over 100 years thinking this compound was basically unmakeable. You're going to learn the real, documented history of a molecule called carbon monosulfide, not a Wikipedia summary. The actual lab notebooks, the actual radio telescope data, the actual 1868 discovery that nobody could explain for a century. You're going to learn why it's one of the most important molecules in modern astronomy, used right now to find where new stars are being born inside galaxies billions of light years away. You're going to learn the physical atomically reason it can't hold itself together outside very specific conditions. And you're going to learn how chemists eventually beat it, how they tamed an unstable compound and turned it into a tool. If you've ever heard the phrase, "this only exists in a vacuum," thrown around loosely in a science video, stick around, because we're about to correct that myth using the molecule that basically defines it. Let's start with a name. Carbon monosulfide chemical formula, CS1 carbon atom, 1 sulfur atom, joined by what chemists call a triple bond. If that sounds familiar, it should. You already know its cousin. Carbon monoxide CO1, carbon 1 oxygen, triple bond. Same architecture, same electron count, same general shape. Chemists call CS the sulfur analog of carbon monoxide, meaning, on paper, they should behave almost identically. And here's the first myth we need to kill. People assume unstable automatically means weak, that the bond itself is flimsy, fragile, ready to fall apart at the slightest disturbance. Wrong, dead wrong. The bond holding carbon to sulfur in this molecule has a dissociation energy of roughly 645 kilojoules per mole. That is an enormous number. That's in the same league as some of the strongest chemical bonds known. Ripping that bond apart atom from atom takes serious energy. So if the bond is that strong, why can't the molecule survive? This is the question that's going to drive the entire video, and I want you sitting with it for a second, because the answer is not what most people guess. It has almost nothing to do with the CS bond itself being weak. It has everything to do with what happens when two CS molecules meet each other. Let's look at the numbers a chemist would actually care about. The bond length between the carbon and sulfur atoms sits at about 1.53 angstroms for reference. That's roughly the width of about 6 hydrogen atoms lined up in a row. An almost unimaginably small distance, but precisely measurable using microwave spectroscopy. The same technique radio astronomers use to detect this molecule from thousands of light years away, which we'll get to. The molecule carries a dipole moment of about 1.98 dPy. I'll translate that in a second, but hold on to that number, because it's going to become the single most important fact in this entire video. A dipole moment is basically a measurement of how lopsided the electric charge is across a molecule. One end slightly negative, the other end slightly positive, like a tiny magnet, except electrical instead of magnetic. Carbon monoxide, by comparison, has a dipole moment of only about 0.11 dBi. That means carbon monosulfide is nearly 20 times more magnetic, electrically speaking, than its cousin carbon monoxide. Why does that matter? Because a bigger dipole moment means a molecule reaches out and grabs its neighbors harder. It's the difference between two magnets sitting an inch apart doing nothing, versus two magnets sitting an inch apart and snapping together. Carbon monoxide molecules can sit next to each other in a gas cylinder for decades. That's literally how welding shops store it. Carbon monosulfide molecules, sitting next to each other. They reach out, grab hold, and don't let go. That's the seed of everything that's coming. Now, before we go further, let's be precise about the myth in our title, because precision is what separates a real science explanation from clickbait. It is not strictly true that carbon monosulfide can only exist in a vacuum in the sense of zero pressure. Nowhere else ever chemists have generated it in laboratories at low pressure as a gas for brief windows of time using specialized equipment. What is true, rigorously, measurably true, is that outside conditions where CS molecules are kept far apart from each other, isolated, unable to collide, it cannot persist as CS. It converts into something else, permanently, almost immediately. And the only environment in the entire universe where far apart and isolated is the natural default state, not something you have to engineer, not something you have to maintain with pumps and valves, is the vacuum of space. That's the real story. Not it needs a vacuum like it's some fragile lab specimen. It's the opposite. It needs loneliness. And space is the only place in existence that gives molecules real, permanent, undisturbed loneliness. Keep that word in your head. Loneliness. We'll come back to it. Let's go back in time. 1868. This is only 3 years after the end of the American Civil War. Dmitri Mendeleev hasn't even published his periodic table yet. That comes the following year. Chemistry as a field is still working out basic questions about how atoms combine. And in a laboratory somewhere in Europe, a chemist runs an experiment on carbon disulfide CS2, a much more common, much more stable compound you might actually recognize from old industrial processes, since it was used historically as a solvent and in the production of viscose rayon. Under certain conditions, exposure to light, or an electrical discharge passed through the vapor, something strange happens. A brownish solid material starts forming where there should just be colorless liquid and gas. 4 years later, in 1872, a second chemist documents the same phenomenon independently. A brown mass, forming seemingly out of nowhere whenever carbon disulfide gets hit with light or electricity. Nobody in 1872 has the tools to know what that brown mass actually is at the atomic level. Spectroscopy exists in a primitive form. X-ray crystallography doesn't exist, that's another 40 years away. Quantum mechanics, which is the only framework that actually explains why this molecule behaves the way it does, doesn't exist for another half-century after that. So for generations, this brown residue is just a curiosity, a footnote. Something that gunks up the equipment when you work with carbon disulfide under light or electrical discharge. Chemists knew something was polymerizing, stringing itself together into long chains, but the intermediate step, the actual reactive molecule doing the damage, stayed invisible. Here's the reveal, and it's genuinely elegant once you see it. That brown solid is what happens when carbon monosulfide, the CS molecule we've been talking about, forms for a fraction of a second, and then immediately, uncontrollably, links up with every other CS molecule near it, chain after chain after chain. The technical name for this process is polymerization, the exact same word used for how thousands of small molecules link into a single plastic. Except here, nobody engineered it. Nobody wanted it. It just happens, spontaneously. The instant conditions allow it. And the polymer that results, the stuff chemists call CS with a little n subscript, meaning an unknown variable chain length, is actually remarkably tough. It doesn't fall apart at room temperature. It doesn't dissolve easily. In fact, studies show this polymer only starts breaking down significantly at around 360 degrees Celsius, at which point it decomposes back into carbon disulfide, the compound that started the whole cycle. Sit with that irony for a second. The parent compound, carbon disulfide, is stable enough to sit in a bottle on a shelf. The polymer it eventually forms, after some very unstable intermediate steps, is stable enough to survive fires that would destroy most organic material. But the molecule in the middle, the actual carbon monosulfide, the star of this video, cannot exist in bulk for more than an instant under normal Earth conditions. It is the unstable middle child sandwiched between two stable relatives. This wasn't fully scientifically confirmed and characterized as the CS molecules specifically responsible until well into the 20th century, when spectroscopic techniques finally caught up to the question first raised by that strange brown residue back in 1868 and 72. That's over 100 years between we see something weird happening and we can actually explain what it is and why. That gap is worth remembering, because it tells you something important about chemistry as a discipline. The compounds that are hardest to study aren't necessarily the exotic, artificially created ones you hear about in headlines. Sometimes they're compounds that have been quietly forming in ordinary labs for over a century, hiding in plain sight as an inconvenient brown stain, waiting for the right instruments to finally ask them what they are. Now let's get into the actual mechanism. Why does this specific molecule do this specific thing? Go back to that comparison with carbon monoxide. Same electron structure on paper, same triple bond, but wildly different behavior. Carbon monoxide is infamous, really, for being chemically stubborn. It's the reason carbon monoxide poisoning is so dangerous. The molecule binds to hemoglobin in your blood and essentially refuses to let go, outcompeting oxygen. That's a story about carbon monoxide being too stable, too content to just sit there bonded to something and stay put. Carbon monosulfide is the opposite personality entirely, and the reason comes down to a detail most people never think about. Atomic size. Carbon and oxygen are both small atoms, sitting right next to each other on the periodic table, in the same row. Their outer electron orbitals are compact and they overlap tightly and efficiently when they bond, producing a genuinely strong, genuinely stable triple bond that doesn't want to react further with much of anything. Sulfur, on the other hand, sits one row below oxygen on the periodic table. It's a noticeably bigger atom, with outer electrons occupying a larger, more diffuse orbital. When carbon tries to form that same triple bond arrangement with sulfur instead of oxygen, the size mismatch means the orbital overlap isn't nearly as clean. You still get a strong bond. Remember that 645 kilojoule figure, but the electron distribution around that bond ends up lopsided and reactive in a way carbon monoxide's electron cloud simply isn't. That lopsided electron distribution is exactly what shows up as the dipole moment we talked about earlier, that 1.98 dBi figure, almost 20 times larger than carbon monoxide's. And a molecule with a strong dipole moment is a molecule that acts like a tiny, sticky electrical hook, constantly seeking out other molecules to interact with. Now put trillions of these sticky, reactive little hooks in the same room, at normal pressure, where they're colliding into each other billions of times per second. What happens? They react with each other, not with the air, not with moisture, not with anything exotic, with more of themselves. One CS molecule's carbon end latches onto another CS molecule's sulfur end. That combination is still reactive, so it grabs a third molecule, then a fourth, then a 40th. Within a fraction of a second, you don't have individual CS molecules anymore. You have that same brown polymer chemists were confused by back in 1868, growing in real time, right in front of you. And this isn't a gentle process. Multiple documented accounts from chemists working with concentrated carbon monosulfide describe the polymerization as explosive, not metaphorically explosive, but genuinely capable of detonating if the monomer, the pure unreacted CS gas, is allowed to build up in any real concentration. This is precisely why, for the better part of a century, chemists treated this molecule as something you observed in trace amounts through a spectrometer, not something you tried to bottle. Here's the piece that makes the vacuum connection click into place. Polymerization requires collision. Two molecules cannot link together if they never touch. In a vacuum, true vacuum, or the closest approximation of it in deep space, the density of matter is so unbelievably low that individual CS molecules can go months, years, sometimes far longer, without ever bumping into another CS molecule. There's simply nothing around them to react with. They're not being protected by some special vacuum-only chemistry. They're just alone, isolated, untouched. Bring that same molecule down to a lab bench at atmospheric pressure, and the density of surrounding matter shoots up by roughly 25 orders of magnitude. 25 orders of magnitude, that's a 1 followed by 25 zeros, roughly the ratio between the width of an atom and the width of the observable universe. At that density, collisions between CS molecules happen constantly, continuously, unavoidably. The molecule doesn't get a choice. It reacts, because there's nothing else it can do. That's the actual physics. Not vacuum as magic. Distance is the entire story, and nowhere in the universe delivers permanent distance between molecules quite like the vacuum of space. Now we get to my favorite part of this story, because this is where carbon monosulfide stops being a laboratory curiosity and becomes one of the most useful tools in modern astronomy. November 1973, a research team led by a radio astronomer named Tucker points the National Radio Astronomy Observatory's 11-meter telescope toward the Orion Nebula, one of the most active star-forming regions visible from Earth, roughly 1,300 light-years away, glowing faintly to the naked eye as the middle star in Orion's sword. They're not looking for visible light. They're listening for radio waves at a very specific frequency, the frequency at which a rotating CS molecule emits a signature spin, a rotational transition, in spectroscopy terms, essentially the molecule's radio fingerprint, and they find it. Clean, unmistakable, coming from deep inside the nebula's gas clouds. For the first time in human history, carbon monosulfide is detected outside a laboratory, not made by a chemist under controlled conditions, but existing naturally, on its own, drifting through the vast, frigid emptiness between forming stars. Think about what that actually means. This is a molecule that, on Earth, self-destructs in a fraction of a second the moment enough of it gathers in one place, and yet here it is, out in the depths of space, in quantities large enough for a radio telescope on Earth to detect its signal after traveling for over 1,000 years across the galaxy. That signal left the Orion Nebula around the time the Byzantine Empire was fighting wars in Bulgaria. It's been traveling, uninterrupted, this entire time, carrying information about a molecule that can't survive a full second down here. Since that first detection in 1973, astronomers have found carbon monosulfide practically everywhere they've looked for it. Dense molecular clouds throughout our galaxy. Small, dark, compact clouds called Bok globules, the actual stellar nurseries where gravity is slowly collapsing gas into new stars as we speak. Active star-forming regions across the Milky Way, the outer shells surrounding carbon-rich evolved stars, dying suns in their final chemical factory phase, comets passing through our own solar system, and even other galaxies entirely, tens of millions of light-years away. But here's the part that turns this molecule from cool space fact into essential scientific instrument. Remember that dipole moment we discussed? That property that makes CS so reactive and unstable down here on Earth. In deep space, that exact same property becomes a superpower. Radio astronomers use something called a critical density to describe how dense a cloud of gas has to be before a specific molecule starts glowing brightly enough at radio wavelengths to detect clearly. Molecules with a strong dipole moment, like carbon monosulfide, need relatively dense surroundings, tens of thousands to over 100,000 particles per cubic centimeter, before they light up properly at radio wavelengths. Carbon monoxide, by contrast, with its tiny dipole moment, lights up at much lower densities, sometimes only 1,000 particles per cubic centimeter. What that means practically is this. When astronomers point a telescope at a giant molecular cloud and see carbon monoxide glowing everywhere, they're seeing the entire cloud, thin gas and thick gas alike. But when they specifically look for carbon monosulfide and it lights up, they know they've found the dense pockets, the specific regions inside that cloud where gravity has pulled enough material together that a new star might actually ignite. Carbon monosulfide, in other words, doesn't just tell astronomers there's gas here. It tells them there's gas here that is dense enough to be on the verge of forming a star. It's a targeting system for stellar nurseries, built entirely out of a molecule that would destroy itself instantly if you tried to hold it in your hand. Researchers using facilities like the Boston University Galactic Ring Survey have specifically leaned on this exact property, using carbon monosulfide emission as a volume density tracer, mapped against carbon monoxide as a broader column density tracer, to build detailed pictures of star-forming activity across huge swaths of our galaxy's spiral structure. There is, to be scientifically honest with you, an ongoing debate in the astrochemistry community about exactly how reliable CS is as a dense gas tracer in the very densest, coldest cores. Some research has shown that in the extreme cold near absolute zero found deep inside collapsing prestellar cores, CS molecules can freeze directly onto the surface of dust grains and effectively vanish from the observable gas for a while, meaning astronomers sometimes now pair CS observations with other molecular tracers to get the fullest picture. But even that complication tells you something remarkable. This molecule is so chemically reactive that it doesn't just react with itself, it can react with dust grains in deep space too. Reactivity is simply this molecule's defining personality trait, whether it's on a lab bench or 1,000 light years from the nearest star. Let's zoom out and take stock of just how widespread this unstable molecule actually is, because the scale here is genuinely staggering, and it directly undercuts the lazy assumption that unstable means rare. Carbon monosulfide has been detected in dark, dense interstellar clouds within our own Milky Way, the raw cold material that will eventually collapse under gravity to form the next generation of stars. It's been found in the outer atmospheres of carbon stars, aging giant stars nearing the end of their lives, where intense stellar winds are actively blowing enriched material, including freshly synthesized carbon and sulfur, out into surrounding space, effectively seeding the galaxy with the raw ingredients for future CS molecules. It's been detected in comets. When a comet swings close enough to the sun, ices on its surface sublimate, releasing gas and dust in a glowing coma. And spectroscopic analysis of that coma has revealed carbon monosulfide as one of the molecular species present, meaning this can't survive outside a vacuum. Compound is quite literally part of the primordial chemical inventory locked inside objects that have been orbiting since the birth of our solar system 4.5 billion years ago, and it's been detected outside our galaxy entirely in other galaxies, sometimes tens of millions of light years distant, using the exact same rotational radio signature first picked up from Orion back in 1973. When you detect carbon monosulfide in a distant galaxy, you're not just confirming, yep, chemistry works the same way over there too. You're getting a density map, a star formation forecast, direct evidence of where, inside that entire galaxy, new suns are actively being assembled right now, or rather, tens of millions of years ago, since that's how long the radio waves took to reach us. Here's a thought experiment worth sitting with. Every single carbon monosulfide molecule ever detected by a telescope has existed, uninterrupted, for as long as it's been drifting alone through space, which, in some of these dense, cold, undisturbed molecular clouds, could plausibly be thousands or millions of years. Meanwhile, the total cumulative lifespan of every gram of carbon monosulfide humans have ever successfully created in a laboratory, across more than a century and a half of trying, probably adds up to less time than it took you to watch this video so far. That's not a knock on the chemists, it's a genuinely mind-bending illustration of just how completely the environment, not the molecule's intrinsic strength, determines whether something can persist. This is the point in the video where I want to push back gently on a framing you'll see in a lot of pop science content. The idea that unstable reactive molecules are somehow weaker or worse than stable ones. That's a human bias, not a chemical fact. Carbon monosulfide isn't a defective version of carbon monoxide. It's a molecule perfectly suited to an environment that is, by an enormous margin, the most common environment in the entire observable universe. 99.something% of the universe, by volume, is closer to vacuum than to anything resembling Earth's atmosphere. From that perspective, you could argue carbon monosulfide isn't the fragile one. Water, air, rock, the stable stuff we're built from, that's the cosmic exception. We are the anomaly. Space is the rule. And carbon monosulfide is perfectly, comfortably adapted to the rule. For most of the 20th century, if you wanted carbon monosulfide, your options were limited. You could generate it briefly, in a low-pressure gas cell, usually by running a high-voltage electrical discharge through carbon disulfide vapor, breaking the CS2 molecule apart and knocking loose a sulfur atom to leave CS behind, or by pyrolysis, essentially superheating carbon disulfide until it decomposes, or through photolysis, using intense light to snap the molecule apart. All of these methods work. All of them produce carbon monosulfide, and all of them produce it in tiny, fleeting amounts, immediately vanishing back into polymer within moments, unless you kept the pressure extremely low and used it or studied it almost instantly. That changed once chemists developed real handling techniques specifically designed around this molecule's self-destructive tendencies. One documented and genuinely clever method: generate carbon monosulfide as a gas, then immediately trap and freeze it using liquid nitrogen. cooling it down to around minus 196 degrees Celsius. At that temperature, the molecules are essentially frozen solid, locked in place, unable to collide and react with each other. Then, and this is the critical part, you deliberately allow it to warm back up slowly, in a controlled way, at which point the polymerization that used to happen instantly and violently instead proceeds in a slower, manageable, more predictable fashion, allowing researchers to actually study and use the material forming as it happens. Later work, some of it detailed in a 1986 doctoral thesis specifically focused on turning carbon monosulfide into a useful synthetic intermediate, pushed this further. Researchers developed specialized handling protocols that let them generate carbon monosulfide in gram quantities, genuinely significant amounts for a molecule that had spent over a century being treated as impossible to isolate, and use it immediately in controlled reactions before it had the chance to polymerize on its own terms. The explosive nature of the pure monomer, extensively documented by earlier researchers who'd been literally hindered by it detonating in their equipment, was specifically what these newer techniques were built to work around. And once chemists could reliably access it, even briefly, carbon monosulfide turned out to be genuinely useful, not just a curiosity to be feared, but a tool. It reacts efficiently with a range of nitrogen and sulfur-containing compounds to build entirely new molecular structures, essentially functioning as a sulfur delivery reagent in organic synthesis, letting chemists insert a carbon-sulfur unit into a target molecule in a single controlled step rather than through longer, more roundabout routes. It's even been coaxed into acting as what's called a ligand, a molecule that attaches to a metal center in specialized transition metal complexes, sitting stably bonded to atoms like iron once it's anchored in exactly the right molecular environment, proving that even this notoriously self-destructive molecule can behave itself completely, provided you give it the right partner to bond with instead of letting it find another CS molecule to grab. There's something almost poetic in that. The same reactivity that makes carbon monosulfide unstable and dangerous in bulk is precisely the reactivity that makes it valuable once chemists learn to control it, direct it, and put it to work instead of letting it destroy itself. Let's go back to where we started, because now you actually have the tools to evaluate that opening claim properly instead of just taking my word for it. This compound can't survive outside a vacuum. Is that true? More precisely true than most viral science claims you'll see online. But it needs one correction, and it's an important one, because it's the difference between memorizing a fact and actually understanding chemistry. It's not the vacuum itself doing anything special. Vacuum isn't a protective force field. What vacuum provides uniquely, reliably, and essentially permanently, unlike anything achievable on Earth, is distance, isolation, the prevention of collision. Carbon monosulfide doesn't need nothingness to survive. It needs to be left alone by copies of itself. Space is simply the only place in existence that guarantees that condition without any maintenance, without any equipment, without anyone having to try. And this distinction matters beyond just carbon monosulfide, because it turns out this molecule isn't even alone in this behavior. Silicon monoxide CO1, silicon atom bonded to one oxygen atom, is thermodynamically unstable relative to breaking down into elemental silicon and silicon dioxide under normal Earth conditions. Yet it's been detected as a genuine gas phase molecule around stellar objects, and it's actually considered the most common oxide of silicon anywhere in the universe, purely because interstellar space gives it the isolation it needs to exist as SEO rather than falling apart into something else. Carbon subsulfide, a related compound, C3S2, is a deep red liquid that, sitting at room temperature on Earth, readily polymerizes into a hard black solid within a relatively short window, following a strikingly similar self-destructive pattern to its cousin, carbon monosulfide. So carbon monosulfide isn't some singular, freakish exception in the chemistry of the universe. It's actually a preview, an especially well-documented, especially well-studied example of a much broader category of molecules that exist perfectly comfortably throughout the cosmos, in the vacuum of interstellar space, while remaining essentially impossible to keep intact in bulk anywhere on the surface of a planet like ours. And that flips the entire premise of this video on its head, doesn't it? We called this the one compound that can't survive outside a vacuum to grab your attention in the first 10 seconds, and it worked. You're still here 50 minutes later, but the deeper, more accurate way to describe carbon monosulfide is that it's a completely normal, stable, unremarkable molecule for the environment it actually belongs to. We're the ones living in the unusual corner of the universe. Down here, on a rocky planet, wrapped in a thick blanket of atmosphere, awash in collisions happening billions of times a second. That's the weird, statistically rare environment. Space, cold and empty and undisturbed, is the default. Carbon monosulfide isn't fragile, it's home. So here's what I want you to walk away with. Carbon monosulfide was first glimpsed, completely by accident, as an unexplained brown residue in 1868, a full century before anyone had the tools to understand what it actually was. It carries a bond stronger than most people would ever guess, roughly 645 kilojoules per mole, and yet it destroys itself in normal air in a fraction of a second, purely because its lopsided electric charge, A dipole moment nearly 20 times stronger than carbon monoxide's makes it grab hold of every other copy of itself it collides with. It was detected drifting through the Orion Nebula in November of 1973, and it has since become one of astronomy's most valuable tools for locating exactly where, inside distant molecular clouds, the next generation of stars is quietly getting ready to ignite. And eventually, after more than a century of being feared as unstable and unmanageable, chemists learned to work with it directly, freezing it, controlling it, and using its reactivity on purpose instead of running from it. The real lesson here isn't really about carbon monosulfide at all. It's about how easily we mistake unstable under the conditions I'm used to for unstable. Period. An entire universe of chemistry is happening right now. In the cold and the dark and the emptiness between stars, following rules that would look impossible from where you're sitting, and yet it's some of the most common chemistry there is. If this kind of deep dive into the chemistry hiding in plain sight, or floating 1,000 light years away is something you want more of, subscribe, because next time we're going into the compound that chemists nicknamed after the devil himself, and trust me, that one's earned it. Thanks for watching, all the way to the end.